This is a joint work together with Johannes, Christian, and Daniel, and I like to start the presentation with the corresponding XKCD comic. So I think we're all familiar with the problem. We are waiting for our code to compile, and while it might be fun some of the time, actually it's quite a problem. Just a quick recap. So it's expensive, it wastes energy, it consumes developer time, and ultimately costs money. The problem is omnipresent, so it's on your toy project, on your laptop, or on large code bases in a CI on a server. So large code bases get multiple changes per minute, which increases the problem. And of course, most of the time it's completely redundant. There's no new value because the compilation that happened before reproduces the same result again, and so we could have skipped this altogether. So of course there are solutions to the problem, timestamp-based incremental builds, for example, like Make does it, but they come with their own problems. Another solution, which I want to talk about today, is compilation caching. So I think most of you are familiar with Ccache, and why I focus on Ccache for this presentation, most of it applies for others for similar tools like sccache or build system integrated functionality in Bazel or Bug. I just think that cHash is the most established and representative for all. So what Ccache does is that it basically just hashes the source code of a translation unit, then puts the hash together with the result of the compilation into a directory. And in the future, if we occur the same source code, so get the same hash, we can just retrieve the compilation output. What I mean with that is the object file from the previous compilation and skip the compilation. This approach works quite nice. So in our testing for incremental builds, we measure the speed up of 10%. But Ccache has its limitations. So first of all, it's sensitive to formatting and white space changes, which maybe it's okay, but the bigger problem is that it reacts to changes in unused code. So if you think about it, most of the time you have your source code, and the source code includes multiple headers, which include transitively more headers and so on. And if a change occurs in any of those headers, no matter if the function is used or not, Ccache will recompile. And also, Ccache only works with C and C++. So there's support for more languages, but the main focus is on C and C++. So these are problematic limitations, and therefore colleagues of mine at USENIX ATC 17 introduced cHash, which works quite similar, but instead of hashing the source code, they hash the abstract syntax tree, the AST. The approach is more precise than Ccache and amounts to a speed up of 16% for the same test that we did to Ccache. The problem is the implementation is highly complex and C-specific. So there were plans to introduce support for C++, but it was deemed too complicated and error-prone. So in theory, you could do it, but you have to get it right, otherwise it's worthless. So, but this raises an interesting question. We've seen two compilation caches using different trade-offs, working on two different levels of abstraction. So yeah, maybe we should put in the work to find the optimal abstraction layer for this kind of work. To do this, let's look at the build time breakdown for the average translation unit when compiling OpenSSL using Clang. So what you can see in total, the average compilation unit takes 70 milliseconds to compile, and the most of the time is spent in 5 different phases. So just a disclaimer, this figure is just an approximation. In practice, the different phases are more intertwined. So what we can see is that first the preprocessor runs, which is quite fast, so handling all the if, def, and includes. Then the parser parses the source code into the AST, which takes with 31 milliseconds a lot of time. Then very short time, 1 millisecond, the AST is lowered into IR. So intermediate representation is an internal language that the compiler uses for the next step, the optimization parsers, which is basically a more powerful assembler. But all the complex, high-level features of the languages are already broken down. So it basically removes all syntactic sugar. And yeah, last part, optimization, quite expensive. So what cCache does is works on the level before and after the preprocessor. So what they do is they hash the source code on as is on disk. But if they have a cache miss, they also run the preprocessor and hash the source code after the preprocessor again. This works. They can save a lot of time because they can skip parser and optimization phases of the compiler. Ccache, on the other hand, runs after the parser, which of course has the downside that the parser has to run, which takes a lot of time, but they make up for it by way more precise than cCache. So of course, now the question is which abstraction levels are left. Of course, yeah, doing a caching after the optimizer has run makes no sense because there's nothing to save there. But yeah, right after IR generation, where the AST was translated into IR, it could make sense to build a compilation cache. So why IR? So of course, while it's the abstraction that is left, but on the other side, there are interesting aspects of it. So first of all, as I said, it's early enough in the compilation that we still have the ability to skip the optimization phase. It's already fairly close to the final compilation results, resulting in high precision, and it's also insensitive to formatting, unused code, and many syntactic variations. Data structures are designed for frequent traversal because that's what the optimizer does. So we can expect high performance and also a plain implementation due to the conceptual simplicity of IR. So in the end, the idea is to get the upsides from cHash and the simplicity from cCache. And there's one final benefit. Multiple compiler front ends for different languages target LLVM IR. So this would mean support for languages like C, C++, Fortran, Haskell, Rust, Swift for free. So as a cherry on top, let's say. Of course, we implemented it as an LLVM parse, so it's basically a compiler plugin that LLVM-based compilers can load. It's less than 600 lines of code, 200 of which are just the compilation, the caching logic. The caching mechanism works similar to cCache, so we just calculate the hash and store the object file in a directory and retrieve it on a cache hit. The hashing works, so IR is hierarchically structured. There's the translation unit on top, which consists of global variables, functions, which again consists of basic blocks, instruction, and each instruction has an opcode and operands, and we just hashed everything top to bottom. The same applies for complex types, which are hashed recursively down to their scalar components. And of course, we made sure that everything works as intended. We validated our implementation on 1.2 million translation units, so we're quite confident about the implementation. But of course, I think you're more interested in performance, so we did this as well. We took 16 open source software projects in 4 different languages. So for C, we have Linux, OpenSSL, SQLite, Lua, Postgres, Python, Bash, MBTS, STL, and Muscle. For C++, we have Box, ASIO, Clazy, Gamma Ray. For Fortran, we have LAPACK, and for Haskell, we have shellcheck. So as you can see, we have applications from different domains to ensure generalizability. And together with the different languages, we have quite a large coverage of language constructs. For each of the projects, we took 100 commits from the development histories to simulate changes to the code base. And we ran our evaluation on an Intel Core i7 with 12 cores with 32 gigabytes of memory to simulate a developer machine. Also, the evaluation took over a week to complete, so we disabled Turbo Boost to handle thermal throttling. So the results. So on the x-axis, you see the different projects. I only depicted half of it because space on this slide is limited, but I think you get the idea. On the y-axis, you can see the average compilation time per commit. And we measured everything for baseline, so not using any compilation cache, Ccache, cHash, and IRHash. As you can see, using a cache generally is faster, which is good. That's the purpose, except for SDL, where Ccache is a little bit slower than baseline. Apart from that, everything is as expected, and IRHash consistently achieves strong results with being the fastest most of the time. Only for bash and embed TLS, cHash is fractionally faster. Of course, you also might be wondering why there are bars missing for Clazy and LAPACK. The reason is that Clazy is written in C++ and Ccache doesn't support cHash, doesn't support C++. And LAPACK, written in Fortran, isn't supported by any of the compilation caches except for IRHash. So, in summary, compared to not using a cache at all, IRHash reduces compilation time by 12 to 53%. But I think more interesting is the comparison to Ccache, where we can save between 5 and 30%, which also means we are always faster than Ccache. And as you can see, we also support more languages. So you might ask yourself, why? How is this possible? Let's look at the precision. So with precision, I mean how many redundant builds. Precision of 100% means no redundant builds occur. And we use the object file hashes as ground truth. As expected, the earlier in the compilation cache works, the less precise are the results. So while Ccache is quite good, there's room for improvement, as we see for cHash and IRHash, which are really close to each other and achieve nearly a perfect score with close to 100% precision. And also IRHash is always the most precise, except for SDL, but I think you won't see it here, where again cHash is ever so slightly more precise. Last, the overhead, and this is where it gets interesting. So with overhead, I mean the time introduced into the compilation by the hashing process. IRHash is on average 2 orders of magnitude faster, has less overhead than Ccache, and 1 order of magnitude compared to cHash. So IRHash has an overhead consistently below 1%. So why is this? Ccache has the problem of having to hash a lot of data because it's the complete source code, including all headers and so on. And also they have to do it twice, once before the preprocessor and once after it in case of a cache miss. cHash, again, it's a little bit faster because the AST is already fairly optimized, but IRHash has the advantage of just using the data structures for the IR, which are way more linearized because it's just code from top to bottom. There are no cross links between AST nodes and so on. That's the reason why the overhead is so good. And you all, again, might be wondering why there are bars missing for SDL and LAPACK. And the reason is, so the bars, they are there, but they are so small because the overhead is just 0.2%. So in summary, we presented IRHash, a generalizable, maintainable, and efficient compiler cache. It supports numerous languages, so we evaluated it on C, C++, Fortran, and Haskell, and we expect it to work on basically everything using LLVM IR, so over 30 different languages. It's quite maintainable with 600 lines of code, which aren't too complex. And it outperforms existing tools in accuracy and speed. So we have a precision of up to 100% and have 2 orders of magnitude less overhead compared to Ccache. And in the end, we are up to 30% faster. You can find the artifacts, so you can repeat everything if you want to online. And yeah, thank you for your attention, and I'm happy to take questions.